The ocean has a distinct smell. Many people associate it with salt, seaweed, or sunscreen. But have you ever noticed a slightly unpleasant, almost sulfuric odor? That pungent aroma comes from a gas called dimethyl sulfide, or DMS. While not exactly pleasant to our noses, DMS plays a crucial role in regulating Earth's climate. This little-known gas, released by marine organisms, embarks on an incredible journey from the ocean depths to the atmosphere, where it influences cloud formation and helps cool our planet. The primary producers of DMS are tiny plant-like organisms called phytoplankton. These microscopic powerhouses drifting in the ocean's sunlit surface waters are responsible for producing over half of the oxygen we breathe.
Phytoplankton synthesize a compound called dimethyl sulfonopropionate, or DMSP. DMSP helps protect these organisms from environmental stress, acting like a kind of cellular sunscreen, an antifreeze, and a salt regulator. When phytoplankton die or are eaten by zooplankton, their DMSP breaks down, releasing DMS into the water.
Once released into the water, some DMS is consumed by marine bacteria. However, a significant portion escapes into the atmosphere, like tiny bubbles rising to the surface of a glass of soda. DMS molecules make their way from the ocean depths into the air above. The amount of DMS released depends on factors like the abundance of phytoplankton, water temperature, and wind speed. Warmer waters and stronger winds tend to enhance DMS emissions, creating a direct link between the ocean and the atmosphere. Clouds are essential for regulating Earth's climate, reflecting sunlight back into space and influencing precipitation patterns. But have you ever wondered how these fluffy white masses form in the first place? Cloud formation requires tiny particles called condensation nuclei.
These microscopic specks of dust, salt, or other aerosols provide surfaces for water vapor to condense onto, forming cloud droplets. Without condensation nuclei, clouds would have a much harder time forming.
This is where DMS comes in. Once in the atmosphere, DMS undergoes a series of chemical reactions, transforming into sulfate aerosols. These sulfate aerosols act as condensation nuclei, providing the perfect platforms for cloud droplets to form. The more DMS in the atmosphere, the more sulfate aerosols are produced, leading to the formation of brighter and more reflective clouds. These brighter clouds then reflect more sunlight back into space, reducing the amount of solar radiation reaching Earth's surface.
It's fascinating how such a tiny particle can have such a big impact on our planet's climate. The idea that DMS released by phytoplankton could influence cloud formation and ultimately climate was first proposed in the 1980s by Robert Charlson, James Lovelock, Meinrad Andreae, and Stephen Warren. Their groundbreaking theory, known as the claw hypothesis, named after the first initials of the author's last names, suggested a feedback loop between the ocean, atmosphere, and climate. This hypothesis was revolutionary at the time, as it provided a new perspective on how marine life could have a significant impact on global climate systems. The claw hypothesis opened up new avenues of research, encouraging scientists to explore the complex interactions between biological and atmospheric processes.
According to the claw hypothesis, warmer ocean temperatures would lead to increased phytoplankton activity and DMS emissions. This, in turn, would result in more cloud formation, reflecting more sunlight and cooling the planet. This elegant feedback loop highlighted the interconnectedness of Earth's systems and the crucial role of DMS in regulating climate. The hypothesis suggested that as the planet warms, the ocean's biological processes could act as a natural thermostat, potentially mitigating some of the effects of climate change. This concept has been a cornerstone in understanding the dynamic balance of Earth's climate system and has inspired numerous studies to further investigate the role of DMS and other biogenic compounds in climate regulation.
It's amazing to think about how interconnected everything is, isn't it? The claw hypothesis reminds us that even the smallest organisms, like phytoplankton, can have a profound impact on our planet's climate. This interconnectedness underscores the importance of protecting marine ecosystems, as changes in these environments can ripple through the entire climate system. As we continue to study and understand these complex relationships, we gain valuable insights into how to better manage and protect our planet for future generations. The story of DMS and the claw hypothesis is a testament to the power of scientific inquiry and the endless curiosity that drives us to uncover the mysteries of our world.
The claw hypothesis, while still debated, has sparked considerable research into the role of DMS in the climate system. This hypothesis suggests that dimethyl sulfide, or DMS, produced by marine phytoplankton, could have a significant impact on cloud formation and consequently, on the Earth's climate. Researchers are delving into how this sulfur compound interacts with atmospheric particles to influence weather patterns. While the exact mechanisms are complex and not fully understood, evidence suggests that DMS does play a significant role in regulating Earth's temperature. Scientists are exploring the various pathways through which DMS affects the atmosphere, including its role in the formation of sulfate aerosols, which are crucial for cloud condensation nuclei. These nuclei are essential for cloud formation, which in turn affects the Earth's albedo, or reflectivity. By influencing cloud formation and reflectivity, DMS acts like a natural thermostat, helping to moderate temperature extremes. Clouds formed with the help of DMS can reflect sunlight back into space, thereby cooling the Earth's surface. This process is particularly important in regulating the temperature of our oceans, which play a critical role in global climate systems.
When temperatures rise, increased DMS emissions can lead to more cloud cover and a cooling effect. This feedback mechanism helps to prevent the Earth from overheating. The additional cloud cover not only reflects more sunlight, but also traps heat, creating a balanced climate system. Conversely, when temperatures drop, DMS emissions decrease, reducing cloud cover and allowing more sunlight to reach the surface. This reduction in cloud cover can help to warm the Earth's surface, demonstrating the dynamic balance maintained by DMS in our climate system.
It's a remarkable natural process that helps keep our planet's climate in balance. The interplay between DMS emissions and cloud formation is a testament to the intricate and delicate systems that govern our environment. Understanding these processes is crucial for predicting future climate changes and developing strategies to mitigate their impacts.
Section 8, the climate change conundrum disrupting the delicate balance. Climate change is already impacting Earth's delicate systems, including the ocean. Rising ocean temperatures, ocean acidification, and changes in nutrient availability are all affecting phytoplankton populations and their ability to produce DMS.
The consequences of disrupting this delicate balance are still uncertain. Some studies suggest that climate change could lead to decreased DMS emissions, reducing cloud cover and exacerbating warming. Others propose that increased ocean stratification could limit nutrient availability for phytoplankton, hindering their growth and DMS production.
Section 9, surprising connections, DMS coral reefs and the atmosphere. Coral reefs, often called the rainforests of the sea, are not only biodiversity hotspots, teeming with a myriad of marine species, but also significant contributors to DMS emissions, a crucial component in the Earth's climate system.
These vibrant ecosystems, home to a dazzling array of marine life, including fish, invertebrates, and algae, release DMS through a surprising source, coral mucus. This mucus is not just a simple secretion, but a complex mixture of sugars, proteins, and lipids, which plays multiple roles in the marine environment. It protects corals from desiccation, pathogens, and harmful UV radiation, acting as a shield against environmental stressors. Additionally, coral mucus serves as a vital food source for various marine organisms, such as plankton and small fish, some of which produce DMS as a byproduct of their metabolic processes. This DMS then enters the atmosphere, where it plays a role in cloud formation and climate regulation. The connection between coral reefs, DMS, and climate highlights the intricate and delicate balance of Earth's systems and the far-reaching consequences of environmental change. As climate change continues to impact coral reefs, the production of DMS and its subsequent effects on the atmosphere could be altered, leading to unforeseen changes in weather patterns and global climate. Scientists are actively studying these connections to better understand the potential impacts and to develop strategies for preserving these vital ecosystems. Conservation efforts are crucial in maintaining the health of coral reefs, ensuring they continue to provide essential services to marine life and the planet's climate system. By protecting coral reefs, we are not only safeguarding biodiversity, but also supporting the natural processes that regulate our climate. Global initiatives and local actions are needed to address the threats facing coral reefs, from pollution to overfishing and climate change. Together, we can work towards a future where coral reefs thrive, continuing to play their vital role in the Earth's interconnected systems.
Section 10. Unveiling the mysteries, ongoing research on DMS and climate. Despite decades of research, many questions remain about the intricate relationship between DMS, clouds, and climate. Section 11. Conclusion. The importance of understanding our planet's intricate systems. DMS, a seemingly insignificant gas with an unpleasant odor, plays an outsized role in regulating Earth's climate.
Its journey from the ocean depths to the atmosphere, where it influences cloud formation and reflects sunlight, highlights the interconnectedness of our planet's systems. Understanding the complex interplay between DMS, clouds, and climate is crucial for predicting the consequences of climate change and developing effective mitigation strategies. As we continue to unravel the mysteries of this enigmatic gas, we gain a deeper appreciation for the intricate mechanisms that govern our planet's delicate balance.